Introduction, the whispering edge of time. There is a silence in the cosmos more profound than any we know on Earth, beyond the hum of distant stars, beyond the shimmer of galaxies swirling in slow motion, lies an abyss of possibility, vast, eternal, and indifferent. It is in this stillness that the greatest stories unfold, not of beginnings, but of endings. From the birth of light in the Big Bang to the tapestry of matter and energy we see today. The universe has always been a stage of transformation, but just as every star eventually fades and every atom finds rest, the cosmos itself may have an ultimate fate, or perhaps many fates layered like alternate endings in a book we have only just begun to read. Imagine a future where time stretches so far that the stars themselves blink out, leaving a black, cold void. Or a moment when the very fabric of space tears apart in a final, cataclysmic scream. What if the universe is devoured, not from without, but from within by forces born in its earliest seconds, waiting patiently through eons for their return? These are not the inventions of science fiction, but the reasoned predictions of cosmologists who peer deep into mathematical equations, seeking clues etched in the radiation of the early universe, in the spirals of dying galaxies, in the chilling quiet between celestial pulses. Each chapter in this journey will unveil a different possibility, some slow and subtle. We will drift through concepts like heat death and vacuum decay, through phantom energy and quantum destruction, each scenario more haunting than the last. But we will do so gently, calmly, in the spirit of curiosity rather than fear. Because to explore the end is not to court despair, is to embrace wonder, to understand the fragile miracle of now. In a universe measured by billions of years and unimaginable distances, our small moment is made more beautiful by its impar, M-A-N-E-N-C-E. So let us begin this quiet voyage to the limits of cosmic time. Let us trace the possibilities that lie at the edge of everything. And as we drift through darkness, may the gentle rhythm of the universe guide us forward, one breath, one thought, one mystery at a time. Chapter 1: The Big Freeze. When the stars go out. The universe is expanding. Galaxies drift farther apart, their lights receding into a deeper night. At first glance, the vastness seems eternal, the stars unending, but nothing in the cosmos is infinite. Not even starlight. The Big Freeze, also known as the heat death of the universe, is one of the most widely accepted scenarios for how everything might end, not with a bang, nor a collapse, but with a long, slow sigh into darkness. It is a future without fireworks, a cosmic silence that descends gradually as energy disperses, and order gives way to entropy, To understand this end, we must understand what powers the universe now. Stars burn through nuclear fusion, converting hydrogen into helium and radiating energy that warms planets and lights the night. Galaxies are dynamic arenas of gravity and motion, where matter clumps, collapses, and ignites in luminous brilliance. But this energy, this vibrant, organized, dances, temporary. Entropy, the measure of disorder, always increases. This is a fundamental law of thermodynamics. With each passing second, the universe moves toward a state of greater entropy. Stars exhaust their fuel. Black holes consume. Galaxies grow quiet. Over time, fewer new stars are born, and those that remain slowly flicker out. One by one, in about 100 trillion years, star formation will cease entirely. The universe will enter the so-called degenerate era, a period dominated not by stars, but by the remnants they leave behind. White dwarfs, neutron stars, and black holes. These stellar corpses will persist for unimaginable spans of time, glowing faintly, whispering of a cosmos that once was ablaze with fire. Even they, eventually, will vanish. White dwarfs will cool into black dwarfs, hypothetical objects so dim they emit no detectable light. Black holes will evaporate through Hawking radiation, a slow leakage of mass that will take even the most massive among them up to 10 years to fully dissolve. Nothing escapes this fate. Not light, not matter, not memory. What remains is a universe in thermal equilibrium. Every point in space the same cold, dark, lifeless temperature. No gradients of energy, no structure to exploit. Without differences in energy, there can be no work. Without work, no processes. It will be the ultimate quiet, the stillness after the longest song. What's most chilling about the big freeze isn't its violence, but its passivity. It requires no dramatic shift, no fatal instability. It simply continues what is already happening. Space expands, stars age, and entropy rises. We are, in this view, already on the long road to cold infinity. There are theoretical curiosities that emerge in this frozen world. Some physicists speculate that, in the deep future, quantum tunneling might cause incredibly rare, spontaneous fluctuations, tiny bursts of order from disorder. Could a particle arise from nothing? Could a brief moment of structure appear like a ripple in silence? Even the strange idea of Boltzmann brains, disembodied conscious moments formed purely by chance in a high entropy universe finds footing in this chilling forecast. But these phenomena, if they ever occur, would be sparse, random, and ultimately fleeting. They would not restore what was lost. they would only underscore the emptiness that surrounds them. The Big Freeze is not a singular event, but a transitions, low, inevitable, and indifferent. It evokes a kind of cosmic melancholy, a future with no future. Yet in this vision of the end, there is also a strange peace. No explosions, no collapse, just the quiet unfolding of thermodynamic law, painting a picture not of cruelty, but of balance. To contemplate this fate is to appreciate the miracle of now. Our universe is in a golden age, brimming with energy, complexity, and light. We are the children of stars, living in a brief but glorious chapter of cosmic history. And while the cold may come, we have the warmth of presence, of thought, of wonder, as we drift onward through this journey of endings. Remember that each catastrophic possibility is also a mirror reflecting back the beauty of the moment we inhabit. The stars may go out someday, but until then, they shine for us. Chapter 2: The Big Crunch, when gravity takes everything back. In the beginning, there was an explosion of unimaginable scale. From a singularity smaller than an atom, space itself unfurled, giving birth to all matter, energy, and the dimensions we now inhabit. This event, the Big Bang, set the universe on a journey of expansion. But what if, at some distant point, that expansion ceased? What if everything we know and everything we are began falling back, collapsing into a final, all-consuming convergence? This is the essence of the Big Crunch, cosmic catastrophe in reverse. It is the idea that the universe, now stretching ever outward, could someday change its mind. Instead of expanding, it would slow, stall, and then contract. Galaxies would begin to drift toward one another, gravity once again reigning as the dominant force in a shrinking cosmos. The distant would become near. The cold would grow warm, and in time, everything would meet in a single, radiant point, just as it once began. The Big Crunch is not merely a poetic inversion of the Big Bang. It is a physically plausible outcome of Einstein's theory of general relativity. Whether or not this scenario unfolds depends on a cosmic tug-of-war between the energy-driving expansion and the collective gravity of all matter in the universe. If the density of the universe is greater than a certain critical threshold, then gravity will eventually win. Expansion will halt. Collapse will begin. Imagine the sky billions of years from now. Instead of galaxies growing more distant, their light stretching red into the void, we would see them moving inwards, lowly at first, then faster and faster. Space itself would shrink. Cosmic background radiation, now faint and cool, would grow hotter as it is compressed. Temperatures would rise, matter would compact, and galaxies would merge into dense, chaotic clusters as the contraction accelerates. The universe would become increasingly energetic and violent. The great cosmic structures, galaxies, stars, planets would be torn apart by gravitational tides. Collisions would dominate the night. Radiation would intensify, and eventually, even atoms would be crushed under the growing weight of the collapsing cosmos. Some theorists suggest the final moment would mirror the beginning, a singularity, a point of infinite density and temperature where space and time break down. In this view, the Big Crunch becomes not merely an end, but a potential seed for rebirth, a new Big Bang, a new universe, possibly an eternal cycle expansion, collapse, expansion again playing out endlessly like the breath of a cosmic being. Others, however, see the crunch as absolute, not a reset, but a terminal state. The laws of physics as we know them may not survive the final singularity. All structure, all memory, all information may vanish beyond the horizon of compression. The end would be total, unobservable. And final modern observations suggest our universe is expanding faster and faster, driven by a mysterious force known as dark energy. This discovery complicates the picture of a potential crunch. If dark energy continues its influence, strengthens the universe may never collapse at all. But theories evolve, and what seems dominant today may be transitory. Dark energy itself remains poorly understood. It may decay, reverse, or behave differently in the far future. There is also a strange comfort in the symmetry of the Big Crunch, a universe that comes full circle. What was spread out is drawn back in. What had form is made formless. It reflects a deep principle seen across nature, birth and death, expansion and contraction, order and entropy, and perhaps in the deepest mathematics of reality. There is balance that cannot be avoided. To consider the Big Crunch is to imagine time rewinding, not backward in experience, but inward in direction, toward a singular reunion. The galaxies, once scattered like seeds in the wind, returning to their source, a silent falling together until all that is one dot as we continue this journey into the universe's possible fates. Let us carry with us this vision, not of destruction alone, but of return. A collapsing universe is not necessarily a dying one. It may be a breath held before the next awakening. Chapter 3: The Big Rip, Tearing the Cosmos Apart. There is a strange force threading through the fabric of the universe, one we cannot see, cannot touch, but whose influence is undeniable. It drives galaxies apart, stretches voids between stars, and accelerates the expansion of space itself. This force, known as dark energy, is one of the greatest mysteries of modern cosmology. And if its power grows unchecked, it may lead the universe not into cold darkness, nor into collapse, but into a violent and final unraveling known as the Big Rip. To envision the Big Rip, imagine the universe as a vast elastic sheet expanding under tension. Now imagine that this tension is increasing, not weakening with time, but strengthening, faster and faster until the sheet tears. Every galaxy, star, planet, molecule, atom, and even the quantum fields that define existence, ripped apart by the expansion of space itself. This terrifying scenario emerges from a peculiar possibility that dark energy is not a constant, but a dynamic force. In most cosmological models, dark energy is described by the cosmological constanto, steady pressure that stretches the cosmos at a consistent rate. But if dark energy is instead a form of phantom energy with a negative pressure even more extreme than we currently suspect, then its influence will not remain steady. It will grow. As phantom energy builds, so does the expansion rate of the universe. Galaxies begin to separate at increasing speeds. Light from the most distant objects disappears into red-shifted oblivion. Over time, gravitational bonds that hold galaxy clusters together are overwhelmed. Galaxies disintegrate. Stars, once bound by the steady pull of gravity, are set adrift. Planetary orbits destabilize. Even solar systems fall apart. Closer to the final moment, the destruction accelerates. The gravitational glue binding planets to stars is severed. Moons drift away. Tidal forces grow intolerable. Eventually, the forces that hold matter itself together, atomic bonds, subatomic particles overcome. Atoms stretch, then snap. Space no longer holds form. Even time itself loses coherence. Cosmologists have modeled this timeline with sobering precision. If phantom energy exists with a particular strength, then the Big Rip could occur tens of billions of years from now. In the last 60 million years before the end, galaxies would scatter. In the final months, solar systems would break. In the last seconds, atoms would be shredded, and space-time would split apart. Not because of heat or collision, but because of raw, unrelenting expansion. This is not an implosion or a freeze. It is an unmaking, a reversal of cohesion. The universe does not fall inward, nor fade away, is pulled apart by the very laws that once gave it structure. The notion of the Big Rip challenges our assumptions about the stability of cosmic laws. We often think of the universe as governed by constant fixed values that define gravity, electromagnetism, and the geometry of space. But phantom energy would represent a breakdown in those expectations, a reminder that what we call constants may only be temporary conditions. There is something uniquely chilling about the Big Rip, not because it ends the universe. Many scenarios do that, but because it ends everything we consider foundational. It undermines not just structure, but meaning. No remnants remain. No cold stars, no burnt-out husks, no whispers in the void. Only absence, a true cosmic blank. Still, this idea remains theoretical. Observations suggest that dark energy behaves more like a constant, at least for now. But the margin of error is small, and the future remains unknown. If phantom energy is real, its quiet accumulation may already be underway. In this possibility, we live in a moment of fragile harmony window where galaxies still exist, where matter still holds, where time still moves. The sky above, filled with distant stars, is a gift of coincidence. A brief phase between the chaos of creation and the shattering of expansion. Let us hold gently the knowledge that our universe, so vast and ancient, is still mysterious. And in contemplating its most violent ends, we also discover how delicately it holds us in place. For now, space is still calm. The stars still shine. But somewhere in the deep equations of physics, the future may already be written. Chapter 4: Vacuum Decay. The silent rewriting of reality. There are ends that roar and ends that freeze. But some, perhaps the most terrifying of all, come silently. The laws of reality. This is the eerie possibility of vacuum decay, a catastrophe not born from heat, gravity, or time, but from the very quantum fabric of existence. To understand vacuum decay, we must descend into the subtle foundations of physics. In quantum field theory, what we call empty space is anything but empty. It is alive with fluctuations, virtual particles that blink in and out of being, fields that ripple with energy, and a delicate balance of forces that allows matter, time, and causality to function. This background state of energy is known as the vacuum state. But like any energy configuration, it can be either true or false. A true vacuum is the most stable, lowest energy configuration possible. A false vacuum, on the other hand, is a local minimum stable under small disturbances, but vulnerable to collapse into something even more fundamental. If our universe exists in a false vacuum, then it is not truly stable. It merely seems stable because we have not yet triggered a transition to the true vacuum. But such a transition could occur naturally or through a quantum tunneling event. It would begin with a microscopic region of space suddenly dropping into a lower energy state, creating a vacuum bubble with different physical constants. And this is where the horror begins. The bubble would expand at the speed of light, unstoppable and completely indifferent to what lies in its path. Inside this bubble, the laws of physics as we know them, those that allow atoms to bind, stars to burn, and consciousness to exist, might be altered, broken, or erased. There would be no warning. The leading edge of the bubble would outrun any signal or detection. From our perspective, the end would arrive instantaneously. One moment, we are here. The next, gone. Not just destroyed, but redefined. What would a true vacuum be like? It's impossible to say. The structure of matter may not exist in the same way. The balance between forces may be disrupted. Electrons might not orbit nuclei. Light might not propagate. Even time itself might unfold differently or not at all. It's not an apocalypse in the traditional sense, Sika. Reconfiguration of reality. Some physicists believe this is more than a theoretical curiosity. When the Higgs boson was discovered in 2012, its measured mass suggested that our universe might, in fact, be sitting in a metastable vacuum state. The exact values of the Higgs field and top quark masses create a precarious balance, like a ball resting, not at the bottom of a valley, but on the edge of a slope. Stable for now, but not forever. Of course, quantum tunneling events of this magnitude are incredibly rare. The timescales involved stretch beyond comprehension trillions upon trillions of years. And yet, the possibility is there, quietly, written into the equations of particle physics. Even more unsettling is that no shielding or defense is possible. Unlike black holes or expanding stars, which can be studied and avoided, a vacuum decay event is non-local. It doesn't spread through space in the traditional sense. It remakes space as it goes. Nothing can escape. Nothing can remain unchanged. And yet, despite its silent terror, vacuum decay is a reminder of how interconnected all things are. Our universe balances on the interplay of forces so precise, so delicately tuned, that even the smallest fluctuation can alter everything. Life, structure, and thought are all possible because of this rare, perhaps temporary, stability. We exist in a cosmic lullaby, quiet interval between extremes. The vacuum hums around us, its energy invisible, yet essential. And in that hum is both our safety and our fragility. As we drift through these scenarios, let this one linger like a whisper. The universe may not end in noise, nor cold, nor fire, but in a flicker of quantum truth, where all things become something else. Chapter 5: Quantum Collapse. When the wave function fails. The universe, for all its vastness and grandeur, is built upon uncertainty. At the smallest scales, reality is not a fixed structure, but a cloud of possibilities, particles that may exist here or there, energies that fluctuate without cause, events that occur only when observed. This strange, probabilistic world is the realm of quantum mechanics, and central to it all is the wave function, the mathematical heartbeat of potential. The wave function describes all the possible states a system can occupy. It evolves smoothly, like ripples on a pond, until it interacts with something, an observer, a particle, a measurement. Then, in an instant, the wave function collapses, and a single outcome is chosen: a location, a spin, a moment of being. But what if the wave function that governs our universe, our entire reality, could collapse? Not in a localized experiment, but universally. Not into clarity, but into disarray. Because the cosmos itself no longer knew how to define itself. This is the eerie possibility of quantum collapse at a cosmic scale. In most interpretations of quantum theory, such as the Copenhagen model, collapse happens during measurement. Yet no one agrees on what exactly constitutes a measurement. Is it the presence of a conscious observer, a physical interaction, a threshold of complexity? And in the vast, empty darkness of the cosmos, where observers are rare and randomness abounds, what then? Some theories propose that the entire universe can be described by a universal wave function, evolving through time like a vast, entangled breath. Everything we know, galaxies, atoms, thoughts, as part of this singular quantum state. But such a wave function may be unstable. Under specific conditions, it could suffer a spontaneous collapse, ending all coherent evolution. Imagine a scenario where decoherence spreads not from interaction, but from an internal breakdown in the laws of probability themselves. Quantum systems, once interconnected, begin to misfire. Entanglement fails. Particles lose correlation. The foundations of cause and effect dissolve into pure noise. The result would not be fiery destruction, nor implosion, but something stranger, fading of coherence. A universe where events no longer follow patterns, where memory and structure dissolve, and where the arrow of time ceases to function. We might not notice it right away. Quantum systems on Earth might begin to drift from predictability, random errors in computation, strange breakdowns in chemical processes. Over time, the disintegration would accelerate. Neurons would misfire. Stars would fail to fuse. The balance of forces that govern everything from electromagnetism to gravity might decay not violently, but imperceptibly. And then, like a dream, ending without waking, the universe would fall into quantum silence. There is a class of theories called objective collapse models that explore this concept. Unlike traditional interpretations where collapse requires observation, these models suggest that wave functions may collapse spontaneously after reaching certain thresholds of complexity or mass. If this process is built into the universe, it could eventually affect systems as large as galaxies or the universe itself. Alternatively, if consciousness plays a role in collapse, then a dying universe with fewer observers may lack the mechanisms to sustain measurement. Reality could slowly unravel not because it is destroyed, but because it is no longer being defined. This possibility touches not only physics, but the philosophy of existence. What is real, if not observed? What remains when all possibilities are equal and none are chosen? In this scenario, death is not violent. It is the erasure of preference, the smoothing of structure into sameness. No heat, no darkness, only uncertainty. The universe becomes a haze of uncollapsed options, waiting eternally for a measurement that will never come yet. This quiet end also reveals something profound. Our role as witnesses. In every observation we make, every particle we detect, we participate in the act of collapse. We help the universe choose. We anchor probability into experience. So as we drift among stars and theories, remember, perhaps the most vital act in the cosmos is simply to see, to measure, to be aware. Because in doing so, we may be the very mechanism that holds the wave function together. Chapter 6: The Black Hole Era. A universe of silent titans in the immeasurable expanse of time. Even the most brilliant stars must fade. Their lifespans, while immense by human standards, are but flickers in the story of the cosmos. And when the final star burns out, a new chapter begins, one not of light, but of gravity. A future shaped not by galaxies and stardust, but by dark, dense remnants of collapsed worlds. Welcome to the Black Hole Era, an epoch where time itself stretches into stillness, and the last great structures of the universe are titanic, invisible prisons of space. This era lies far beyond our current age, trillions upon trillions of years. In the future, by then, all stars will have exhausted their fuel. Most will have died quietly, becoming white dwarfs neutron stars, or fading embers lost in the dark. Some will have gone violently, collapsing into black holes, regions of space-time so warped by gravity that not even light can escape their grasp. In the black hole era, these gravitational giants will dominate the cosmos, isolated. Eternal lore, so they seem, each one the collapsed core of a once mighty star, containing within its event horizon a singularity, a point of infinite density where the known laws of physics break down. Though they emit no light, black holes are not entirely inert, thanks to the insight of Stephen Hawking. We now know that black holes slowly radiate energy, process known as Hawking radiation. Over unfathomable periods of time, they lose mass ever so gradually, until they eventually evaporate into nothing. But this process is slow, incredibly slow, for a stellar mass black hole. The evaporation could take over 10 years, a number so large it's nearly beyond comprehension. For the supermassive black holes at the centers of galaxies, the timeline stretches further to 10 years or more. And so the universe, once vibrant and teeming with stars, will settle into quietude, with no new stars forming and all matter either fallen into black holes or drifting alone in the void. Activity will cease. The galaxies we see today will have unraveled, their stars gone cold or consumed. Black holes will remain as the last actors on the stage of existence, motionless and slowly dying. The interactions between these black holes may continue for a time. In some cases, they might collide, merging into even larger entities. But these events will grow increasingly rare until gravitational interactions become vanishingly unlikely. The cosmos will stretch wider, colder, and more empty. Time will continue, but change will not. Eventually, Hawking radiation will complete its slow work. One by one, black holes will fizzle out in a final whisper of heat. Not an explosion, not a blaze, but a last faint shimmer of radiation, the death sigh of space-time curvature. And with the final evaporation, a profound stillness will fall over the universe. What remains then? No stars, no planets, no particles. Just a thin, cold sea of low energy, photons and elementary particles spread across an ever-expanding space. This is the degenerate era at its most complete. Nothing more than ghost-like radiation drifting toward absolute zero in this era. Entropy reaches its pinnacle. The universe trends toward heat death, a state of maximum disorder where no work can be done, no memory can persist, and no structure can form. Time itself becomes meaningless as nothing changes. Nothing evolves. Everything simply is, and yet there is a strange elegance in this silence. The black holes, once thought to be eternal tombs, are revealed to be temporary beacons of gravity. Even they yield to the laws of quantum mechanics. Even they must end. The black hole era is a reminder that the cosmos is patient, that time stretches not in millennia nor in eons, but in powers of unimaginable magnitude, and that, in the end, not even darkness is forever, too, must fade. But here, in this distant vision of the future, we glimpse the ultimate humility of matter. Everything, every galaxy, every planet, every thought will end not in fire nor in collapse, but in the slow evaporation of silence. Chapter 7: The Heat Death of the Universe. When time loses meaning. There are endings that strike swiftly through collapse, fire or fury. And then there are endings that arrive like the slow settling of dust, creeping not with violence, but with inevitability. The heat death of the universe is such an ending, not a bang nor a whimper, but a gentle descent into stillness. The final chapter in a cosmos where every process, every movement, every memory quietly fades. To grasp this concept, we must first revisit the nature of entropy, the measure of disorder, randomness, and the number of microscopic configurations a system can have. In every closed system, entropy tends to increase. Stars burn fuel, planets cool, and galaxies drift apart. Energy spreads out, differences even out, and structure dissolves. The universe itself is the ultimate closed system. From the moment of the Big Bang, it has been evolving, stars forming, elements fusing, black holes devouring matter. But with each interaction, usable energy capable of doing work becomes less available. Over time, systems fall into thermal equilibrium, where all temperatures are balanced, and no more work can be extracted. This is the essence of heat death, a state in which the universe reaches maximum entropy. Everything is the same temperature. No gradients exist. No processes can occur. Matter is diffused. Light is stretched thin, and all motion slows to a halt. It's not a dramatic end. Rather, it's the absence of all drama in this far future. Universe. Stars have long since died. Black holes have evaporated through Hawking radiation. What remains is a dilute soup of subatomic particles and cold radiation spread so thin across space that any interaction becomes effectively impossible. Photons with wavelengths longer than galaxies drift endlessly through expanding space. Temperatures hover near absolute zero. The arrow of time, once guided by the increase of entropy, now becomes meaningless because entropy can increase no further. There is no clock in this final silence, no event to mark one moment from the next. The universe continues expanding, but this expansion carries nothing with it, only emptiness, stretched thinner and thinner. Some theorists describe this as the final thermodynamic equilibrium state, where everything is at rest, not because it has been destroyed, but because there is no more energy to be transferred. Every possibility has been exhausted. Every transformation has occurred. And now only stasis remains. This vision is chilling, not for its violence, but for its inevitability. It is rooted in the second law of thermodynamics, one of the most dependable principles in physics. Unless a mechanism exists to reverse entropy on cosmic scales, a possibility unsupported by current science, the march toward heat death is not just possible, but likely. It is a future devoid of observers. Because observation requires contrast between states, between energies, between before and after. And in heat death, there is no before, no after, just sameness everywhere. Always, the implications go beyond physics. If life is the manipulation of energy to sustain structure, then heat death represents the death of possibility itself. No new thoughts, no new patterns, no complexity. Not because it has been erased, but because the stage on which complexity could arise has been dismantled. And yet, in this ending, there is a strange peace. No cataclysm, no destruction, just rest. The universe, after eons of birth and death, creation and collapse, simply releases its last breath into silence. We often imagine the universe as eternally active, forever evolving. But in this perspective, activity is a phase, one that has a beginning, a middle, and ultimately an end. The cosmos began in fire, expanded in complexity, and will end in stillness. And perhaps, from the viewpoint of time itself, this final equilibrium is not death, but balance, quiet. Balance that can never be disturbed again. Chapter 8. The Big Rip. When the fabric of space tears itself apart. The universe is not still. It is stretching, expanding, moving outward in all directions. Galaxies drift apart like leaves on a rising tide, carried by the invisible current of space itself. For billions of years, this expansion has shaped the structure of the cosmos. But what if this gentle drift were not so gentle? What if the expansion didn't just continue, but accelerated faster and faster until it tore everything apart? This is the haunting possibility known as the Big Ripper hypothetical end to the universe, driven not by collapse or cooling, but by runaway expansion. A cosmos so overwhelmed by its own growth that it cannot hold itself together. At the heart of this idea lies one of the greatest mysteries in physics: dark energy. This elusive force is believed to make up about 68% of the universe. It acts in opposition to gravity, driving galaxies away from each other at increasing speeds. We see its effects in the redshift of distant galaxies and in the cosmic microwave background. But we do not know what it is. In most current models, dark energy is described as a cosmological constanta, fixed energy density that causes a gentle but steady acceleration. If this remains true, the universe will expand forever, slowly growing, colder and more diffuse. But there is another possibility. What if dark energy is not constant? What if it becomes stronger with time? In a variation of dark energy called phantom energy, the repulsive force doesn't just stay steady, it increases. As the universe grows, so does the energy driving its expansion, and the consequences of that acceleration become catastrophic. At first, galaxies would be pushed farther apart. Clusters would become isolated, unable to see each other through the stretching void. Then, gravitationally bound systems like the Milky Way would begin to break apart. Stars would drift from stars, planets from stars, moons from planets. In the final moments, the acceleration would reach smaller and smaller scales. The solar system would unbind. The Earth would drift away from the Sun. Tidal forces would shred planets into dust. Eventually, atoms themselves could be pulled apart. Molecular bonds would fail. Electrons stripped from nuclei. Even the fundamental particles of matter could be torn asunder, ripped from the structure of space-time as the very metrics of the universe diverge to infinity. And all of this could happen in a finite amount of time. In some models, this final rending might occur as soon as 20 to 30 billion years from now, depending on the strength and behavior of phantom energy. It would begin gradually, almost imperceptibly, but as the end drew near, the effects would cascade rapidly, galaxies unbinding millions of years before the end, stars disintegrating thousands of years prior, planets hours before, and atoms. In the final seconds, the last instant of the universe would not be a silent fade, but a sudden and violent shattering of all structure. The fabric of space would tear. Time would cease to have meaning. And every form of matter would be obliterated not by collision, but by expansion itself. And then there would be nothing. No fragments, no particles, no space to hold them, no time to contain them. just the infinite stretch of a fabric that can no longer support the notion of existence. The Big Rip is speculative but grounded in real physics. It depends on the true nature of dark energy, something we are only beginning to understand. Observations of supernova, galactic motion, and the cosmic microwave background help constrain the possibilities. But the door remains open to this ultimate unraveling. It is a vision of the cosmos, not as a place of eternal decay, but as one racing toward an end it cannot escape. A universe where every moment brings us closer to disintegration, not because of external forces, but because of its own expanding heart. Yet, even in this terrifying scenario, there is beauty. A reminder that the universe is not static, but dynamic. That existence itself is fluid, flexible, and vulnerable to the laws it obeys. And as we look into the night sky, watching galaxies retreat into the abyss, we can wonder, is this the calm before the unraveling, or just another ripple in the infinite story of space and time? Chapter 9: Vacuum Decay. The fragile illusion of reality. Reality feels solid, predictable, governed by laws that have held since the beginning of time. Gravity pulls, light travels, atoms bond. The fabric of existence appears stable. But what if it isn't? What if everything we know, space, time, matter itself, is built on a delicate illusion, one that could collapse without warning into something entirely alien? This is the eerie proposition of vacuum decay, a cosmic catastrophe, not of fire or ice, but of quantum instability. At the heart of modern physics lies the quantum field, a framework in which every particle is a vibration in an invisible field that permeates space. One of these fields is the Higgs field, which gives particles their mass. But quantum fields are tricky. They can settle into different energy states, much like a ball resting in a valley. Most stable is the true vacuum, the lowest possible energy configuration. But sometimes a field can become trapped in a false vacuum, a valley that is low, but not the lowest. And that's where the danger begins. Some physicists believe that our universe may currently reside in such a false vacuum. According to calculations involving the mass of the Higgs boson and the top quark, two particles detected at CERN's Large Hadron Collider, our vacuum might be metastable. That means it's stable enough for now, but not forever in this scenario. A more stable state, the true vacuum, does exist, but it's separated from our own by an energy barrier. Quantum mechanics allows for the possibility that, through a process known as quantum tunneling, a tiny bubble of this lower energy state could form somewhere in the universe, and then everything changes. this bubble of true vacuum would expand at the speed of light, consuming the false vacuum around it. It wouldn't be a violent explosion, but a wave of absolute transformation. As it passed, the fundamental constants of nature forces, particle masses, even the speed of light could change. Chemistry would break. Atoms might dissolve. Life, as we know it, would cease to exist in a fraction of a second. No warning. No time to react. Not even light could outrun the edge of the bubble. The truly haunting part, because the bubble would move at light speed, we'd never see it coming. One moment, everything would be normal. The next, the laws of physics would have rewritten themselves, and the new universe inside the bubble, it might not be hostile, might simply be different. Perhaps structures could form, perhaps not. Perhaps it would support complexity, or maybe collapse into simplicity. We simply don't know. The true vacuum could represent a more fundamental reality, one where our own version of physics is just a temporary mirage. Is this just theory? For now, yes. But it's a theory rooted in the mathematics of quantum field theory and the standard model of particle physics, most successful model we've ever devised for describing the subatomic world. And while it's entirely possible our vacuum is perfectly stable, the fact that it might not be is enough to stir the deepest existential unease. Vacuum decay doesn't require a trigger. It's not a result of human technology or cosmic collision. It could simply happen anywhere, at any moment. The early universe, filled with higher energies, may have had a greater chance of triggering it. But even now, the ticking of quantum uncertainty continues. Yet in this deeply unsettling possibility lies a strange sense of serenity. For if such a fate awaits us, it is completely beyond control. Silent, instantaneous, and universal. No suffering, no chaos. Just transformation of everything. And perhaps, in the vast silence that follows, a new cosmos would unfold. With new laws, new structures, maybe even new minds to ask, once again, what the universe is made of. Chapter 10. The End of Time Itself. When the clock stops ticking, time flows. Or, so it seems, we mark its passing with clocks, with orbits, with aging. We feel it move forward, never backward. But what is time, really? And what happens when the very structure of the universe no longer supports its passage? In this chapter, we delve into a possibility so foreign, so profound, that it transcends even destruction, the idea that time itself could come to an end. Not through the annihilation of matter or collapse of stars, but through a cosmic stillness, so complete that motion, change, and sequence lose all meaning. To begin, we must understand that time, in physics, is not an independent force. It is intimately tied to change. When things move, when energy is transferred, when entropy increases, we perceive time. Time is the measure of change. But what if nothing changed? Imagine a universe stretched thin, billions of years beyond our era. Galaxies are no longer visible. Stars have all burned out. Even black holes have vanished into quantum vapor. Remains is a haze of particles, radiation near absolute zero, and the slow drift of dark energy continuing to expand the void. In this setting, entropy is near its maximum. No structures remain to decay. No differences in temperature exist to generate motion. The universe has reached thermal equilibrium, a state where everything is the same everywhere. In such a state, nothing happens. No events, no evolution, and therefore no time. This isn't merely poetic. In theoretical physics, the idea that time could emerge from change is a serious proposal. In certain interpretations of quantum gravities, such as the Wheeler-Erdewitt equation, time vanishes entirely from the fundamental description of the universe. The laws that govern the most basic components of existence don't need time at all. They are timeless in these models. Time is a macroscopic illusion, a byproduct of the entanglement and evolution of complex systems. It's real to us because we experience sequences, memories, and causality. But those features rely on the presence of entropy, gradients differences that allow for heat flow, decay, and life. When the universe reaches its final, frozen equilibrium, those gradients vanish. There are no more clocks to tick, no more chemical reactions, no more stars to set or rise. The arrow of time, that one-way direction from past to future, stops pointing anywhere. It ceases to exist, not because it is broken, but because it no longer has anything to guide. Some physicists describe this future as the cosmic. Quiet is a term that evokes both silence and cessation. It's not that time ends as in hitting a wall. It's that time loses meaning. Without events, there's no distinction between one moment and the next dot. In this universe, the phrase, "What time is it?" becomes meaningless. There is no before or after, only stillness. Even quantum fluctuations, the jitter of particles in the vacuum, fade into insignificance in a space so vast, so diluted that nothing can interact meaningfully. Time is not destroyed, it is dissolved. For sentient beings, this vision is alien. We are creatures of rhythm, biological, astronomical, and atomic. Our memories, our experiences, our entire sense of identity is linked to the forward motion of time. To imagine a cosmos where that motion halts is to confront the limits of what it means to exist. And yet, this possibility arises not from mysticism, but from logic, from the laws of thermodynamics and quantum theory. It is, perhaps, the ultimate destination of a universe that has exhausted its own capacity for change. No more beginnings, no more endings, just dot. And in that eternal isness, there is a strange kind of peace, a universe that has finished telling its story. Every note played, every particle danced, every wave collapsed. And now, the silence between the stars has become the final chapter, a place, not a time, but a condition beyond both. Chapter 11. The Collision of Brains. When universes crash in higher dimensions, beyond what we can see, beyond the stars and galaxies, beyond even the boundaries of our familiar four-dimensional reality, there may exist something more, a realm of higher dimensions, a landscape not of planets or nebulae, but of membranes or brains, vast multidimensional surfaces on which entire universes, like ours, may be suspended in this framework known as brain cosmology. Our universe is not all there is. It is just one three-dimensional brain floating in a higher dimensional space called the bulk, and we are confined to it. Everything we know, light, matter, gravity, exists within the brain, like paint on the surface of an invisible canvas. But we are not alone in the bulk. There could be other brains, invisible to us, floating just beyond reach. Parallel universes coexisting in dimensions we cannot perceive. And sometimes these brains might collide. This is not science fiction, it's one of the boldest predictions of string theory and M theory, which attempt to unify all fundamental forces under a single mathematical framework. These theories allow for the existence of extraspatial dimensions, curled tightly or stretching infinitely. And in some scenarios, the Big Bang itself was not the beginning of time, but the result of a cosmic collision between brains. Imagine two immense, invisible sheets drifting through a higher dimensional space. Their surfaces approach each other slowly over eons until, at some point, inevitably, they touch. That contact unleashes an immense amount of energy, lighting up the brains in a blast of creation. A new universe is born not from nothing, but from the kinetic violence of two brains coming together. Some cosmologists propose that this has happened not once, but many times. That our universe is one in a cycle of brain collisions and rebirths. A cosmos with no true beginning or end, but rather a rhythm of contact and expansion. But what if it happens again? If another brain exists near ours in the bulk, and if their relative motion continues, it is possible that a future collision could occur. To us, it might appear as a sudden, unstoppable influx of energy and event horizon sweeping through space. annihilating structure and rewriting the fabric of reality. Unlike vacuum decay, this would not be a quantum phenomenon. It would be classical, physical, a crashing together of entire realities. The geometry of our universe could be transformed, the constants of nature altered. Space-time itself would be shaken to its foundation. There would be no defense, no warning. The brain could arrive from a dimension perpendicular to all we know, and the impact would unfold across the entire cosmos simultaneously. One moment, everything is as it has always been. Different, even more intriguing, is the possibility that this brain collision is scheduled, that it's part of a regular cycle. In the ekpyrotic model, a version of brain cosmology, the universe goes through endless cycles of expansion, contraction, and collision. Each collision creates a Big Bang. Each expansion gives rise to stars and galaxies. An eternal heartbeat of the multiv. In this view, the end of our universe is not an end at all, but the prelude to rebirth. A cosmic inhale and exhale. Life may be extinguished, but the stage is set anew for structures to rise again in the next cycle. A phoenix-like vision of the cosmos. Still, the violence of such a collision is unimaginable. Time, as we know it, might reset. What emerges on the other side could bear no resemblance to what came before. We may never detect the presence of another brain. The bulk is silent, hidden from our instruments. But perhaps there are clues than the cosmic microwave background in gravitational waves. In the geometry of the universe itself, that hint at this greater structure beyond our perception. And as we drift through space, unaware of the silent approach of another universe, we are reminded of our fragility, of how small our home is in the greater landscape of possibility, of how, in the vast theater of higher dimensions, the stage itself might shift beneath our feet. Chapter 12: Proton Decay and the Dissolution of Matter. All things decay. Stars fade. Atoms rearrange. Mountains crumble. But beneath these visible changes lies a belief that some things are eternal, that the very building blocks of matter, the proton, the positively charged heart of every atom, stable, immutable, forever. But what if they're not? In the world of particle physics, there lingers a quiet possibility that protons decay, that even the most fundamental components of matter slowly, imperceptibly break apart over time. If this is true, then no structure, no object, no trace of matter in the universe will endure. Given enough time, everything will vanish. The concept of proton decay emerges from the pursuit of grand unified theories, or guts. These are bold attempts to merge three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force into a single, elegant framework. Such unification, if real, suggests that at incredibly high energies, not seen since the early universe, particles can transform in ways we've never observed. One of these transformations is proton decay. According to certain guts, protons are not truly stable, but only appear so because their half-life, the time it takes for half of a given number to decay, is unimaginably long. Some theories predict a proton half-life of around 10 years. That's a trillion times the current age of the universe. If that sounds reassuring, consider this: even such a glacial process, given enough time, would reduce all matter to nothing. Not just stars or planets, but you, me, the atoms in ancient stones, the molecules in frozen galaxies. The physical world would disintegrate from within, one proton at a time. The decay itself would be subtle. A proton might spontaneously transform into lighter particles, a positron and a neutral pion, for example. The pion would then quickly decay into photons, energy from mass, quietly released, invisible to our senses. Such a process has never been observed. Detectors like Super Kamiokande in Japan watch for the telltale signs of a proton decay, event flashes of light deep underground, but so far none has been conclusively detected. Yet, with each passing year, the theories tighten. The silence, too, is informative. If protons do decay, their half-life must be even longer than we thought, but still finite. This matters because it places a boundary on matter itself. It tells us that even in the far future, when stars are gone, black holes have evaporated, and time stretches into unimaginable vastness, will not last. The universe, once luminous and vibrant, will fade not just into darkness, but into emptiness. There will come an age, perhaps after 10 years, when every proton in every remnant of every atom has decayed. Molecules unravel, crystals fall apart. Iron, diamond, DNA, all erased. The last cold matter dissolves into a sea of ghostly particles. Electrons, photons, neutrinos. A low-energy fog drifting across the stretched and silent cosmos. In this final stage, the universe is still expanding, but it carries nothing recognizable. No atoms, no structures, no mass. The matter era, the time when the universe was shaped by tangible things, will have ended. Only radiation, entropy, and space will remain. Is this the fate of everything we know? Perhaps, and yet, there's a strange calm in this vision. Proton decay doesn't explode or burn. It is a slow unmaking, a cosmic sunset that takes trillions upon trillions of years to complete. And still, it raises profound questions. If the very foundation of matter is temporary, what does that say about permanence, about identity, about existence? The universe may not end with a bang, but with a dissolution so slow, so thorough, that it erases the possibility of remembering what once was. And yet, somewhere within this possibility lies a quiet reverence for the present. For now, the protons in your body endure. The atoms in your room persist. The universe still holds together, but in the farthest reaches of time, beyond imagination, even that will fade. The last proton will decay, and with it, the last whisper of form will dissolve into the cosmic wind. Chapter 1-3 The Big Rip. When the fabric of the cosmos tears apart, the universe is expanding. That much we know. Galaxies drift away from one another, carried by the stretching of space itself. For decades, astronomers believed that this expansion might one day slow, perhaps even reverse. But in 1998, everything changed. Observations of distant supernova revealed something unexpected. Not only is the universe expanding, it's doing so faster over time. This acceleration, driven by a mysterious force we call dark energy, changed our vision of the cosmos. And among the possibilities it revealed, none is more haunting than what cosmologists have come to call the Big Rip. To understand the Big Rip, we must first consider what dark energy truly is, rather what we think it might be. It appears to act as a kind of cosmic anti-gravity, pushing galaxies apart with increasing speed. It doesn't thin out as the universe expands. In fact, in some versions of the theory, it gets stronger. If this force continues to accelerate, and if its strength increases without bound, then the fabric of space itself may reach a breaking point. The expansion would eventually become so extreme that it doesn't just move galaxies, it tears them apart, and then stars, and then planets, and finally, the very atoms that make up everything. Let us imagine this future. At first, it seems distant and abstract. Galaxies slip away, redshifted into invisibility. The night sky grows darker. The Milky Way, long since merged with its neighbors, floats alone in the void. Stars continue to burn, oblivious to the deepening pace of expansion. But then subtle changes emerge. The gravitational bonds holding galaxies together begin to weaken. Clusters dissolve. The stars within galaxies begin to feel the pull not from gravity, but from space itself, stretching with ever-increasing force. Over time, the very gravity that holds a solar system intact is overpowered. Planets spiral away from stars. Moons escape planets. The orbits that once marked time dissolve into chaos, and it continues. Eventually, the force of dark energy overtakes the strong nuclear force, the powerful glue holding protons and neutrons together. When that moment arrives, matter is undone. Atoms unravel. Electrons are stripped from nuclei. Even the particles themselves might disintegrate. Unable to resist the tidal expansion of space, the universe, in its final moments, would not be a place of cold quietude, it would be a storm of disintegration. A cosmic rending in which everything we've ever known is pulled apart by space itself. The math behind this is deeply theoretical. It depends on a specific type of dark energy known as phantom energy, whose density increases as the universe expands. If phantom energy exists and dominates the cosmos, then the timeline to destruction could be calculated. In such a model, the universe might continue expanding normally for tens of billions of years. Then, in the final billion years, galaxies fall apart. In the last few million, star systems are destroyed. In the final hours, planets and moons break down. And in the last seconds, atoms themselves come undone. Everything, every particle, every photon, every last thread of structure gone, and then a singularity of expansion. A final, infinite moment when space stretches beyond meaning, a concept of distance, time, and existence itself rips away. The Big Rip is not a certainty. In fact, it's one of the least certain endings for the universe. We still don't know the exact nature of dark energy. It might be constant, it might fade, or it might be something else entirely. But if the conditions are just right or wrong, this is where it all leads. What makes this scenario so uniquely unsettling is that it does not end in fire or cold, but in separation. A disconnection of everything from everything else. A universe that expands so fast that nothing, not even the smallest building block of matter, can hold itself together. Still, in our present moment, the galaxies shine, the stars burn, and space, while stretching, does so with a gentleness we can barely feel. But far in the future, there may come a time when every bond is broken, and in that final tear, the last whisper of matter fades into the infinite. Chapter 14. Death by Gamma Ray Burst. The cosmic flash that ends worlds out there. In the vast, silent stretches between galaxies, death travels at the speed of light. It does not roar or warn. It does not announce its presence with a slow pull of gravity or the curling of time. It arrives instantly as a pulse of raw energy, brief and blinding, yet powerful enough to strip the sky from a planet and sterilize its surface forever. This is the danger of a gamma ray burst, the most violent and luminous explosion known to exist in the universe. When massive stars collapse or two neutron stars merge, the release of energy can be focused into narrow beams that cut through the cosmos like swords of radiation. These beams, only millimeters wide in the grand scale of space, can travel for billions of years and still retain the power to unravel DNA, boil oceans, and destroy atmospheres. They are not science fiction, they are real. Gamma ray bursts, or GRBs, come in two main forms. The first is long duration, typically lasting from a few seconds to several minutes, and originates when a supermassive star collapses into a black hole. The other, shorter bursts, last less than 2 seconds and are believed to come from neutron star collisions so dense and energetic they create not only GRBs but also gravitational waves and heavy elements like gold. But both kinds share a terrifying trait: collimation. Instead of exploding in all directions, much of their energy is funneled into concentrated beams. And if one of these beams is pointed at us 7 from halfway across the galaxy, the consequences could be catastrophic. Earth has been lucky, but there is some evidence to suggest that we may not have always been so fortunate. Some scientists believe a mass extinction event hundreds of millions of years ago may have been triggered by a distant gamma burst. The sudden loss of the ozone layer, a collapse of the food chain, a climate shift so fast it left no room for adaptation. GRB wouldn't need to touch Earth directly. The high-energy photons would hit the upper atmosphere first, ripping apart molecules, creating a chemical cascade that breaks down ozone. Within seconds, ultraviolet radiation from our sun would pour in unchecked, burning the surface, sterilizing oceans and shattering ecosystems. And we would never see it coming, because gamma ray bursts travel at light speed. We receive no warning. By the time our instruments detect the first wave of photons, the event has already begun. There is no defense, no shield, only the hope that Earth's orientation and distance keep us just outside the beam's reach. The most powerful GRBs observed have released more energy in a few seconds than the sun will emit in its entire lifetime. They outshine whole galaxies. Some last mere moments, others linger, flickering across deep space before fading forever. And they are not rare. Astronomers observe dozens every year. Most come from distant galaxies, safe, silent, harmless to us. But a GRB within our own Milky Way, if pointed our way, could end complex life on Earth without a sound. Just a flash, a pause, and then the slow unraveling of everything that depends on atmosphere, chemistry, and biological complexity. To make matters worse, we don't fully understand how to predict them. We know that ultraviolet stars, massive, hot, and nearing the end of their lives, are candidates. Some exist within just a few thousand light-years of Earth, close enough to matter. But stars don't die on schedule, and space does not post warnings. The fear of gamma-ray bursts lies not just in their power, but in their silence. They do not stretch time or tear space. They do not boil over like supernova or creep in like black holes. They are flashes, clean, sudden, unstoppable, and yet, within this darkness, there is still a strange beauty. Gamma-ray bursts forge elements. They help seed the universe with the ingredients for planets and life. They may be deadly, but they are also part of the same cosmic dance that created stars, solar systems, and perhaps even us. So we drift on, beneath a sky sprinkled with quiet. Stars, most will live long, gentle lives. But a few, scattered across the heavens, harbor fire, too intense for any world to survive. We may never see one. We may never feel one. But somewhere in the cold black sea of space, the next gamma-ray burst has already begun its journey, racing outward, unseen, silent, unstoppable. Chapter 15. Cosmic Strings. Slices of space-time that could destroy everything in their path. Imagine a line infinitely thin, unimaginably dense, and older than the galaxies themselves. It doesn't shimmer. It doesn't glow. It cuts across the universe in silence, like a scar left over from the first fraction of a second after the Big Bang. This is a cosmic string, not a string in the traditional sense, but a defect in the very fabric of space-time stretched across. The cosmos, with the potential to unravel anything in its path. Cosmic strings are theoretical, but their origins lie deep in our understanding of symmetry. Breaking a process that took place when the universe was still forming. Just as water freezes into ice, the early universe underwent transitions as it cooled, changing the nature of space and the forces within it. In this transformation, imperfections may have formed, flaws, threads, strings. These strings are not made of matter. They are topological defects, similar in concept to cracks that form when crystals solidify too quickly. But these cosmic cracks would be infinitely long and so dense that just a single mile of one would outweigh an entire planet. And they don't sit still. Cosmic strings, if they exist, move at nearly the speed of light, whipping through the vacuum of space. They generate powerful gravitational effects, not by mass alone, but by distorting space-time itself. Like blades, they don't collide with objects so much as slice through them. If one passed through Earth, the damage wouldn't just be physical. It could warp gravity, collapse structures, and release enormous bursts of energy. Perhaps enough to tear the planet apart in moments. But that's just the beginning. Some theories suggest cosmic strings can form loops, which oscillate and shrink, radiating gravitational waves across the universe. Others may intersect, reconnecting like rubber bands and snapping violently. An event that could send a gravitational ripple strong enough to be detected across billions of light years. And then there's the most terrifying possibility of all. The cusp. At the point of a cusp, a cosmic string folds momentarily upon itself, forming a region of near infinite energy density. If such a cusp were to aim toward Earth, the burst of radiation and gravitational distortion could sterilize entire regions of space. It would be brief, unseen, and it would leave no time for reaction. Despite their destructive potential, cosmic strings might also hold secrets to the structure of the universe. Some models connect them to string theory, hinting that their existence could unify quantum mechanics and gravity. Others suggest they may act as lenses, bending light around them in sharp angles and creating duplicate images of stars and galaxies in the sky. So far, we've found no direct evidence of them. But astronomers continue to search for sudden gravitational waves, for strange patterns in cosmic microwave background radiation, for lensing events with no visible lens. The silence isn't proof of safety. It may simply mean the strings are distant. For now, the unsettling part is that we wouldn't know they were coming. A cosmic string could cross light years in seconds if one were slicing through the galaxy. Right now, its wake might already be en route, invisible and unstoppable. There would be no flash, no warning, only the sudden distortion of everything's space, time, matter-reshaped or erased by something thinner than an atom and older than the stars. Yet in this mystery lies beauty. Cosmic strings may be remnants of the earliest universe fossils from a time when forces were unified and reality itself was still congealing into form. They remind us that the cosmos is not only vast, but deeply textured, filled with unseen seams and ancient memories encoded in space-time. Perhaps they are real, perhaps they are myth. But either way, they urge us to look deeper, to listen to the silence between stars, to watch the sky not only for light, but for the shadows of something that has always been there, unseen, moving, eternal. Chapter 16. False Vacuum, Decay. The collapse of reality itself. There is a possibility, quiet, invisible possibility, that the universe we live in is not entirely stable. It functions. It breathes stars into existence. It allows for matter, for chemistry, for life. And yet, beneath this elegance, physics whispers of a hidden flaw, a cosmic imperfection, so fundamental, so deeply embedded in the nature of everything, that, if triggered, it could erase the universe as we know it instantly. This is the haunting idea of false vacuum decay. To understand it, we must revisit the foundation of quantum physics. In the vacuum of space, the apparent emptiness between galaxies, there is energy. Not the absence of energy, but a field with structure governed by the laws of quantum fields. The lowest possible energy state of that field is called the true vacuum. But what if, instead of resting in the true vacuum, our universe is perched in a false vacuum state of minimum energy that is not truly the lowest? Imagine a marble resting in a small valley. It feels stable. But if there's a deeper valley nearby, and the marble somehow finds a way to roll into it, the system has changed. The marble has found a more stable state. Our universe may be that marble resting in a temporary valley, unaware that a deeper, more stable configuration of physical laws waits elsewhere. If this is true, then the universe is not permanent. It is metastable. It can fall, and when it falls, it would not be gentle. False vacuum decay would occur when a small region of space spontaneously shifts into the true vacuum. This new phase would have different physical constants, different particles, different forces. It might not support atoms, or light, or life. This bubble of altered reality would expand at nearly the speed of light, devouring everything in its path. We would never see it coming, because it moves at light speed. No information can outrun it. The moment the wavefront touches a region of space, the very laws of physics inside that region are rewritten. Time, matter, even the geometry of space may be fundamentally changed or obliterated, and it would begin without warning. A random quantum fluctuation, a shift in a vacuum field at some remote location in space, and the transformation would begin, quietly, invisibly. A bubble expanding faster than thought. What triggers such an event? That is still unclear. Some models suggest that high-energy particle collisions like those in the early universe, or perhaps in advanced experiments could, in theory, push the vacuum over the edge. Others argue that natural cosmic evolution could one day lead to this shift without any external cause, and still, some physicists believe that it may already have happened somewhere, far beyond our observable horizon. The transition to true vacuum may have already begun. The bubble may be expanding now, silently approaching. And we would have no way to detect it until we are already part of it, or no longer are. It is perhaps the most peaceful apocalypse imaginable. No pain, no fire, just instant transformation. From our perspective, reality would simply end. One moment, there's Earth. A heartbeat later, the laws that allow Earth to exist are gone, replaced by something utterly alien, or by nothing at all. And yet, this scenario is not meant to instill fear, but perspective, because false vacuum decay is not evil. It is not malicious. It is a property of nature, quantum possibility written into the structure of the cosmos. A reminder that the laws we trust, the constants we measure, the particles that form our bodies, are not necessarily fixed. May be conditional upon a vacuum that holds, and so far it does. Stars shine, atoms endure. Space hums with the same patterns that have guided galaxies for billions of years. The false vacuum, if it is false at all, holds steady, quietly, calmly, offering a home for thought and time and wonder. Perhaps someday the bubble will form. But until then, we drift in this valley of almost stability, sheltered in a universe that works, that allows dreams and questions and the strange, beautiful possibility that even the end of all things can begin with the softest, most silent flicker in the dark. Chapter 17, The Great Filter, a silent catastrophe that explains our cosmic loneliness in a galaxy of hundreds of billions of stars, with planets swirling around nearly every one of them. The silence of the universe feels unsettling. Where are they? The civilizations, the signals, the signs of cosmic intelligence. We scan the skies and we listen, but we hear nothing. Just static, just stars, just space. This profound silence is at the heart of the Fermi paradox, the mystery of why. In a universe so vast and seemingly full of potential for life, we have found no evidence of it beyond Earth. One possible explanation chills the mind. More than any other, the idea that somewhere along the path from simple matter to spacefaring civilizations, there exists a barrier, a step so difficult, so unlikely, or so deadly, that almost no one ever passes it. This barrier is called the Great Filter. It may lie behind us in the distant past. Perhaps life itself is extraordinarily rare. Maybe, out of all the worlds that could be, Earth was among the few where molecules assembled into living cells. If that's true, we are a miracle, and the Great Filter has already been overcome. But what if it lies ahead? What if the true challenge, the true filters, still waiting? Not in biology, but in civilization, in technology, in what we choose to do with our power once we gain it. Perhaps, as civilizations grow, they reach a tipping point. They create tools too powerful for their wisdom. They discover energy sources that can destroy worlds. They build artificial minds that outgrow their makers. They alter ecosystems so drastically that collapse becomes inevitable. The silence around us may not be the absence of life, but the echo of life that has ended. Civilizations that rose, dreamed, reached for the star's end, then disappeared, wiped away by the very forces they unleashed. That is the terrifying essence of the great filter. Not just death, but self-inflicted extinction, a quiet repeating. Tragedy across the stars, it could take many forms. Nuclear annihilation, runaway, artificial intelligence, ecological collapse, bioengineered pandemics, or perhaps something we haven't even imagined, yet something tied to knowledge so advanced it becomes dangerous by its very nature. And here we are, a young species, intelligent, curious, powerful, peering outward, building machines, sending signals, hoping to find friends in the dark. But the more we look and the more we find nothing, the more one thought lingers. Maybe we're the first, or maybe we're next. Still, there is hope within the theory. If the great filter is behind if life itself is the hard part, then we may be on a lonely but survivable path. A rare flame in a dark forest. If it lies ahead, then the warnings are clear. We must tread carefully, thoughtfully. We must recognize the burden of our knowledge and the fragility of our world. The great filter is not just a theory. It's a mirror. It asks us who we are and what we will become. It reminds us that survival is not guaranteed and that the stars may be full of life that simply didn't make it far enough. But perhaps we can. Perhaps we must. Because in that silence, there's also opportunity to be the first, to learn what others could not, to step past the filter and become the voice that finally breaks the cosmic quiet. Until then, we drift curious, listening, wondering, and the stars wait. Chapter 18: Heat Death of the Universe. When all energy is spent, the universe hums with energy. Stars burn, galaxies spin, particles dance in endless motion. But what if one day all of that motion slows down? What if the great cosmic engine gradually runs out of fuel? This is the haunting vision of the heat death future, where the universe reaches maximum entropy, and no energy gradients remain to sustain motion or life. To understand heat death, we must grasp the concept of entropy, measure of disorder or randomness. In every physical process, entropy tends to increase. Hot things cool down, energy spreads out, and systems move toward equilibrium. The universe began in a state of extremely low entropy, highly ordered, hot, dense. Over billions of years, energy flowed from this ordered state to more disordered forms. Stars burned fuel, black holes formed, galaxies collided, but entropy is relentless. And eventually, the cosmos will approach a state where all energy is evenly spread. No stars will shine. No engines will turn. No gradients will exist to power motion or life. The universe will become a cold, dark, silent place of vast expanse where particles drift aimlessly, unable to do work or create structure. This slow, inevitable fading is not dramatic. It's a gradual, peaceful unwinding. An eternal night where the clock runs down and time itself becomes meaningless. For space, for sleep. This quiet end can be a moment of reflection, a reminder that all things change, and that even the grandest dances must conclude. Yet, heat, death, is not the end of possibility. In the immense timescales involved, quantum fluctuations or unknown physics might intervene. Perhaps new universes will bud forth, or new laws will arise. For now, we imagine a cosmos stretching into the infinite, future fading gently into silence, holding its final breath until the next great beginning. Chapter 19. Big Crunch. The universe collapsing back on itself. Imagine a universe that breathes expanding, stretching space, pulling galaxies apart in a cosmic dance. But what if that breath slows? What if expansion halts and then reverses? This is the vision of the big crunchy cosmic finale, where gravity overcomes expansion, and the universe collapses inward toward a final singularity. In the early 20th century, the Big Crunch was considered a likely fate. Scientists pictured the cosmos as a pendulum swinging between expansion and collapse, a rhythmic cycle of birth and death. Gravity, the great sculptor, pulls all matter together. If enough mass exists in the universe, it could halt expansion and reverse it. Galaxies would slow, stop, and start moving closer, stars drawing nearer. Skies filling with new constellations as cosmic distances shrink. The final moments would be dramatic as space contracts, temperatures rise, matter compresses, forces unify. The universe ends in a singularity, point of infinite density and temperature. Where known physics breaks down, some theories suggest that after the Big Crunch, a new Big Bang might ignite a rebirth, a cosmic reset. This cyclic universe offers a rhythm to eternity, a cosmic heartbeat repeating through time. Yet, current observations suggest that the universe's expansion is accelerating, making the Big Crunch less probable. Dark energy pushes galaxies apart faster and faster, driving space toward a cold, endless spread. Still, the idea of the Big Crunch invites us to imagine a universe that closes its eyes and exhales, returning all matter and energy to a single point, ready to begin again or end forever. For now, it remains a beautiful possibility, an echo of a cosmos that breathes in and out, in rhythms deeper and older than we can fully grasp. Chapter 20: Vacuum Metastability Event. The ultimate cosmic transformation. Imagine that the very fabric of reality is like a delicate balanced, taut canvas, stretched over a cosmic frame. Now imagine that this balance is fragile. A slight ripple, a tiny fluctuation, could tear through this canvas and change everything. This is the idea of a vacuum metastability, eventa, sudden, fundamental transformation where the vacuum state of the universe shifts from its current form to a more stable one, altering all physical laws. In quantum field theory, the vacuum is not empty. It is a field of energy, a state where particles and forces emerge. If our vacuum is only metastabla, temporary valley in the landscape of possibilities, then it could decay to a lower energy state at any moment. When that happens, a bubble of new vacuum would form and expand at the speed of light, rewriting the laws of physics as it spreads. Atoms, forces, and even the structure of space and time would change. This transformation is absolute. It is not survival. It is not change within the universe, no warning, no escape. This is the ultimate cosmic catastrophe, beyond human comprehension. For now, this event remains theoretical, based on our best understanding of particle physics. It may never occur, or it may be billions of years away. Yet, it reminds us that the universe is dynamic, mysterious, and ever-changing in ways both beautiful and terrifying. Finale: embracing the cosmic unknown. As we reach the end of our journey through cosmic catastrophes, we find ourselves humbled by the vastness and complexity of the universe, from silent filters that shape civilizations to the subtle decay of the vacuum, from the fading heat of all energy to the collapse and rebirth of space and time. Each scenario is a reminder of the fragile, fleeting nature of existence. Yet, within this fragility lies profound beauty. We are witnesses to a universe in motion, a cosmos filled with wonder, mystery, and infinite possibilities. The end is not merely a conclusion, but a part of the eternal dance of creation and destruction. So, as you drift into rest, let these cosmic tales inspire awe and peace, for we are here, now, in this moment of time and space live, curious and connected to the grand story of everything, and in the quiet of the cosmos, there is always hope.